Hi all, thanks for joining this session. In this session, I will try to give you an answer on a very interesting question for machine learning workloads running on top of Kubernetes and consuming GPUs. This question also gained huge traction and attention by the Kubernetes community overall. So we at SAP Artificial Intelligence were also very interested in finding an answer. In this session, I will not only give you an introduction how the provisioning of GPUs work, but also share our findings, implementation, and outlook, how you could get started already today in answering the question whether sharing GPU to multiple containers is feasible. But first a little bit about myself. I'm currently working as developer at SAP Artificial Intelligence, mainly on infrastructure-related topics for machine learning and continuous delivery. I have been actively contributing to community projects of Terraform and Cloud Foundry, and the most important, I combine the two worlds of Germany and Turkey with the German beer and Turkish kebab by living in Germany and having Turkish roots. If you want to have a virtual coffee with me after the session, feel free to DM me on Twitter or over the conference platform. I'm really looking forward to chat with you. So, regarding open source, SAP is a platinum sponsor of the Cloud Native Computing Foundation. We at SAP are committed to contribute to open source. So we do this with projects such as Gardener, Kuma, or for the Kubernetes world, but also for the Java world with the Java submachine or Luigi. And feel free to check out these projects. And about artificial intelligence, we care a lot at SAP about artificial intelligence and work on different business services which are later directly consumed on the AI platform or embedded into a large product portfolio. Our vision is to build the intelligent enterprise by embedding step-by-step, easy-to-consume machine learning services running on top of Kubernetes. One of the most consumed services or document information extraction you can see to the right, where we can extract information from invoices. With that and many other services, we run a very serious number of models in production Kubernetes, which not only consume CPUs, but also GPUs for machine learning inference.
So for machine learning workloads, it's most of the time we are using GPUs, and GPUs are a very expensive workload. This is also what we have seen in the production environment of ours. The GPU is also a challenge. Meaning, if I look into our production environments and seeing GPUs only average utilization of 70% makes me really feel sad about it, because why we are not able to fully utilize the GPU. So on the right side, I did some fictional calculation on how much one can lose actually if we run about 500 GPU models for an average price of $3. And you can see that one can actually use about $300,000 per month when running on GPUs, 500 models on an average GPU utilization of 70%. And this is a challenge. So at SAP, we asked ourselves how we can improve the situation. Can we actually share a GPU to improve the situation? So we asked ourselves whether the sharing of GPU in containers is feasible. So in general, at SAP, we are using GPUs from nvidia. And I think in the machine learning area, this is also widely adopted. Talking about GPUs, I asked often myself back then how the magic works behind the scene. How does a device made available to Kubernetes so Kubernetes can consume it, and in the end, how it's consumed by the pod. There has been a great work done back in Kubernetes 1.10, the so-called device plugin, where everyone and every vendor can provide its own custom device. This could be a GPU, an FPGA, or your own custom device, such as Bitcoin miner, could be consumed by containers. The contributors put a great work here to lower the boundaries of accessing custom devices. So let's check it out. Let's keep it general and imagine we are on a worker node. As we all know, each of our nodes is running kubelet or node agent, which is responsible for a variety of things such as spawning our containers and keeping them running and talking to the Kubernetes master. If we now attach our own custom device to our node and we want to make it not only consumable, but schedulable through Kubernetes itself, we need to install the vendor's device plugin, which is actually a simple gRPC server running on every node where we have and want to offer our custom device. Once the device plugin is deployed through a usual deployment through Kubernetes, the vendor device plugin does some initial hardware initialization. For example, finding the hardware, loading the driver, etc. Once done, it registers itself it registers itself by calling register and passes the resource identifier we already have seen on our pod specification, consisting of a vendor name and the device name. Once done, Kubernetes will register the given device plugin and the offered resource and continue on requesting more details on the number of available resources and also identifiers. While Kubernetes regularly checks the health status of the device IDs, the given devices, the device IDs are used before container creation and passed by Kubernetes through the allocate function to the device plugin. During the allocate function, the device plugin prepares the device, marks it internally as used, and returns back data, which is crucial for the container to consume the device correctly. So the key function to be implemented in a device plugin are the functions allocate, register, and list and watch. So let's have a look on what happens behind the scenes once I deploy a machine learning model to Kubernetes, which requests an NVIDIA GPU. In the swimline diagram, you can see to the most right, or GPU, to the left, most right by the device plugin, then our workers and our master node. In the first stage, as discussed before, our device plugin does some hardware initialization by discovering the GPUs which are attached to the node. Once done, it registers itself in the second stage at Kubernetes. And interestingly, is that Kubernetes reports back to the master node the availability of the new device as just advertised by the device plugin, if not already done by other device plugins which are running on other nodes. Upon that, Kubernetes gets data about the available devices on the node from the device plugin in the third stage. The device plugin makes all GPUs unique and returns back their IDs. As Kubernetes is now aware of the number of available GPUs on the nodes, it reports the count back to the master, because the master needs to know what is available to schedule the TensorFlow model A, which are just submitting as a user. Once Kubernetes receives the request to schedule the model, it allocates in stage 4 a GPU, given that the user requests a GPU. And then the NVIDIA device plugin returns the environment variable NVIDIA visible device GPU with the GPU ID, which is later then passed to the container, which can directly access the corresponding GPU within the container. And at this point, where it gets very interesting for our implementation. And actually, this was the whole magic provisioning a GPU. Back then, we actually shared our initial thoughts, findings, and implementation approaches with the community in many comments. Thanks again here for Thomas Jungblut working with me on this topic. Back then, we identified 3 possible variants on sharing a GPU. The first, which was already in place, is the model stuffing on application logic, where we bake multiple models into one Docker image and use TensorFlow serving to switch between these. This very static approach does not offer any C groups for each model, but the whole model, and in addition to that, extended features such as rate limiting per model is not possible. The third variant has been the node selector hacking, and you hear it is hacking. We do not use the device plugin at all. We give the container the privilege mode, which you should never ever do, and let the containers use the GPUs on their own. The drawback of this approach is that Kubernetes does not really know that there are GPUs and cannot respect them during the scheduling. And a very large problem is that Kubernetes might schedule pods on your node even though you do not have any GPUs left. In the end, we have decided for variant 2. Well, it was not really a decision, but more exploration, and with the initial help of some developers from the NVIDIA device plugin. The variant 2 tries to solve this issue in a more native way by extending the device plugin by so-called vGPUs. To be honest, vGPUs sound very terrific, but they are not. So let's check out how we extended the device plugin to share some GPUs. So the problem in general was that once the GPU ID is allocated, it is marked as used by the device plugin. And so no more devices are advertised from a kubelet to the Kubernetes master. In other words, any deployments requesting GPU will be pushed back as requirements cannot be met. In addition to that, we knew from node selector hacking and model stuffing that the GPU can actually handle multiple processes accessing directly to the GPU. So we started thinking about how we can do that. Why we shouldn't advertise more GPUs if there's even only one GPU. So a solution was that simple. we generate, using the GPU ID of a physical GPU, a number of virtual GPUs by simply adding a suffix. Afterwards, we assign those vGPUs in the device plugin to the physical one and tell Kubernetes that we own more GPUs with a GPU ID. So we lie. Once Kubernetes calls the allocate function, we simply remap the virtual GPU ID to a physical one, and that's it. But as simple as it sounds, we have quite a few trade-offs of this approach. It already starts with a problem: how many vGPUs can we or shall we provision per GPU? How do we set the limit? And are there any boundaries with regards to the core and GPU memory? So we ask ourselves following questions. How many models can we fit on an NVIDIA K80? We are running our machine learning inference models on a K80. How does the whole system behave, and what are the trade-offs in doing so, and limitations, of course? So we did our experiments and collected data. Talking about collecting data, the device plugin is nothing more than a pod accessing the local devices to advertise resources to Kubernetes, meaning that the very same strategy of pods for monitoring and collecting data can be used here too. So we extended the NVIDIA device plugin, which internally uses the NVIDIA management library to collect additional data from the devices. And the NVML library actually offers low-level access with CoC binding. So in the end, we created a few Grafana dashboards with the data we got from Prometheus to track different values, such as number of virtual GPUs, we consume GPU per RAM per vGPU, and the GPU utilization. So we have collected data, we have a proper question, and so we did some experiments to answer those. So let's check out our experiments. In the first experiment, we do the well-known and body simulation. While it is not really comparable to machine learning inference, it still gives us some insight on how the work might be distributed internally. And amazingly, to the left, we can see that the G-flops per second are distributed evenly with every pod we just added. This pair scheduling is also confirmed by our data to the right, where the amount of time for an experiment to finish grows linearly with the number of pods accessing a vGPU. Keep in mind that we did not limit the vGPU nor the GPU utilization, and have given every pod a fair share of CPU from the node P2X large at AWS we were running on. While the experiment is kind of comparable to machine learning training, we were more interested in sharing GPUs in the case of machine learning inference. Actually, it includes more factors, such as network, throughput, and latency. So let's check out those experiments we have done. In general, forgot to say this, we are running all of our experiments on a P2X large instance, which has 4 cores and 1 NVIDIA Tesla K80 attached with 12 GB RAM. As the Inception v3 model was used back then for a large amount of our production workload, we use it to thrive our experiments. In the first very inference experiment, we spawned in total up to 12 vGPUs and sent in total of 10,000 requests per pod and limited each pod with 350 amp CPU. We will see later how important in our implementation the limiting of CPU actually is. A disclaimer at this point, this experiment is done using a sequential request pattern, meaning each model handles at most 1 request at a time. Given the data to the left, for 12 models running on 12 vGPUs, we have a P99 in response time below 500 milliseconds. You might be asking how we managed to fit 12 Inception models onto one K80 with 12 GB RAM, while most of the time a model wants to allocate the full GPU. For that matter, we used a very nice functionality of TensorFlow serving. And in TensorFlow serving, one can specify using tf.gpu options the fraction of GPU RAM a model is limited to. Given our data to the right, you can see that with 12 models running on one K80, we assigned each model only 5% of available VRAM, which corresponds approximately 600 megabytes for each model. Another approach was to offer vGPUs until our memory is full to get the most of the vGPU. But actually, we were very keen about finding the upper limit, how many models can be run without crashing on a 1K80. So we ask ourselves, can we go actually deeper? And hell yeah, the Inception model v3 model requires at most 228 megabytes per model. So it's theoretically possible to stack up to 50 models on one GPU. Due to the CPU limitation on our P2 instance, we could run this experiment only for 30 models with a CPU limit of 100 M. and assigning the 3% of the virtual RAM we are having on our GPU. Keep in mind that this is still sequential request pattern. Nevertheless, the 30 models or P99 response time worsened only by factor 10 compared to a single deployment. In our opinion, this is an amazing way to keep models running which do not have large spikes in the amount of incoming requests. These were quite some interesting results, but we also evaluated, of course, the parallel request pattern. And keep in mind, we are still on our P2 setup with the Inception v3, but this time we let the model process 10 requests at a time. We did not enable batching here to establish a baseline where we could later on compare with batching. When we start our experiment for one deployment to establish a baseline, we were able to observe that increasing or decreasing the CPU limit will also limit our GPU utilization. So simply stated, we introduce an artificial bottleneck here for the GPU utilization. This has a huge impact as we can avoid with the CPU limit an overcommitment of the GPU. In general, we have observed that an overcommitment will lead to a large increase in latency. So the equation is really simple in that regard. If you increase your throughput, the GPU has more work to do. So given the limit of 350 amp for the CPU and 3% VRAM, we were able to have 10.7 queries per second at the GPU utilization of 50% for one deployment. For two deployments, we were successfully able to fully utilize a GPU at about 98% and achieved more than double of a QPS for a similar latency. Enabling batching, we could even decrease the latency and increase the throughput by 2 times in exchange for 6 times more VRAM. Given all these data, we ask ourselves again, is sharing to GPU to multiple containers really feasible? Well, in Germany, Germans, after seeing all of these results, would say, "Jein," which is a slang for yes and no, or in other words, in our world, yes, you can share with GPU, but we have trade-offs and accept at least for this implementation some limitations. So after having so many figures and numbers, you were asking yourself, okay, what happened now here? So what does it all mean for our implementation? To be clear and honest here, our solution is far away from production readiness. But we were still able to share our GPU with very promising results. But for that result, we really tried hard. We had to do a lot of runs to find out how much VRAM we actually need, and what are the minimum limits are, and what is the relationship between GPU utilization, CPU limitation, and throughput and latency. Nevertheless, we were able to save up to 30 times of our cost for Inception v3 models running on top of K80 for machine learning inference. Besides the lock into TensorFlow serving for inference, due to the inability to limit virtual RAM from a device plugin, we had to misuse Kubernetes CPU limits to artificially limit our GPU utilization. While this is very hacky and not really Kubernetes native, we were still able to deploy multiple models with very similar latencies by fully utilizing our GPU. And remember the calculation, GPU utilization was a problem. And with that, we actually can fully utilize our GPU. So we have saved some money to buy us some things with our 300,000K. Well, there are of course other limitations besides the control of virtual RAM and GPU utilization. The first and foremost is that we do not really have a clue about what happens on the GPU level when we run multiple processes. We assume that there is some sort of fair scheduling mechanism which we could find out by our experiments. But still, given the fact NVIDIA cannot guarantee isolation on hardware level, it does not make sense for us to run GPU sharing in our multi-tenancy setup. Moreover, we are simply not able to specify the VRAM and GPU costs, which makes it very hard to use native Kubernetes scheduling to schedule pods. Speaking about scheduling, we do our scheduling driven by the number of virtual GPUs. It is not Kubernetes deciding using some detailed sub-resources such as cores and VRAM, but it's only using vGPUs, where we are responsible on deciding how we map our GPU to vGPUs. And another very simple problem is the resource fragmentation. Even if we have GPU sharing, where we have isolation and also maybe possibility to specify limits on VRAM and GPU costs, we are still unable to bin pack our models correctly. because Kubernetes returns to the API server aggregated information, and it does not see the GPU as a first-class citizen. So it can happen that during the scheduling of a workload, a GPU might get overcommitted if there are multiple GPUs running on the same node. For this problem, we would have need a locality-aware scheduling mechanism implemented at the NVIDIA device plugin, which avoids the overcommitment of GPUs. So now, what do we really need to run GPU sharing in production? We need isolation on GPU level. The GPU device driver should offer an API to specify VRAM and GPU cost constraints per process, like we had in C groups. We already see in CPU and memory. At the current point of time, NVIDIA doesn't support any solution with regards to that. But we discussed before, resource the fragmentation of equipment. We need a device plugin which is able to manage sharing of multiple GPUs on one node by being locality aware and avoiding overcommitment of GPUs. And another chapter we did not really discuss at all is the initialization overhead when we spawn a vGPU, but also how fast can a device plugin switch processes which are using the GPU. And of course, last but not least, we need those limits to actually use native Kubernetes scheduling, where people can just specify in their pod, which limits they want to have on the machine learning model. And I have to tell you that our community is actually amazing. Since our initial proposal on the issue, there have been 4 projects trying to solve this issue, where even one very promising was released after the original date of the session. So let's check them out. The first project is Diplomatic. It uses the same approach like we do and lets the user specify the number of vGPUs to be proposed to the user. Using TensorFlow serving and CPU limits, one could realize the very same setup like we did in this session. The second project is from Tencent and called GPU Manager. It internally uses another project developed by Tencent called the CUDA controller, which is a wrapper around the NVIDIA device library, hooking up on CUDA calls to enforce isolation. To the right, you can see that you are then able to specify limits akin to the GPU. Moreover, it requires to add a custom scheduler extender to extend the default Kubernetes scheduler for a GPU admission. Last year, the newly released work KubeShare, which also enforces hardware isolation by intercepting CUDA calls at GPU and implementing an own scheduling mechanism. While GPU Manager requires the extension of Kubernetes scheduler, we see from Tencent, KubeShare coexists as controller and solves a lot of the aforementioned problems with custom resources. We have also written a paper about the approach, showing the approach and their results. I would recommend you to check it out. It gives a very comprehensive insight into the world of containers, scheduling, GPUs, and GPU sharing. If you are planning to contribute or implement at your company GPU sharing, you should definitely check out those projects and contribute to them. At this point, I wanted to give a big thanks to all of these people contributing to the ecosystem we already have. And with that, we are actually coming to the end of this session. Thanks for having me here. Feel free to contact me on GitHub, LinkedIn, or Twitter /SummitGuiana. I'm happy to answer your question. Hi all, so thanks for joining the session. I'm now going to answer a few questions I got here. So the first question is from Josh. He's asking, based on the fact that NVIDIA can't see a way to get C group equivalent GPUs into wide, will this remaining unsolved keep this very niche and outside of upstream? So this has something to do with the device or with the NVIDIA device we actually use. So for example, NVIDIA has announced the T4 devices, which are allowing up to 7 GPUs or 7 workloads on one GPU. So we have, in our experiments, we have used K80s to do this, and the K80s at the current state does not support. And I'm not believing that K80s and also V100s are going to support GPU soon or at any time. Therefore, we have also these great works I've just shown you, for example, from KubeShare, which are trying to solve this by implementing an own a scheduling mechanism on a lower level. Let's go. I hope this answers the question. Let's go on the next question from Clément. Is it usable on GKE? There's already a kubelet device plugin on them. Does it bypass it? So the device plugin is just a daemon set you install on the nodes which are actually having NVIDIA GPUs. And as far as I know, you can also uninstall existing device plugin. This shouldn't be a problem. So yes, you could use any of the open source projects to install on a GKE cluster with GPU sharing. Another question is by Jab. I always thought that context switching between processes slowed down GPU processes. From your experiment, it seems like you've disproven this. Does this have anything to do with the software you're using for serving, or is context switching not big of a problem anymore? I have to be honest here. So because we are trying to solve the problem on a very high level, on the device plugin level, we do not really know what happens on the GPU level. I strongly assume that there's some kind of trashing behavior, that processes are stopped and then new processes take over of the available capacity of the GPU. But to be honest here, I do not really know. But it's really amazing to see that context switching is actually not a big deal. Yes. So I hope that answers your question. There's another question. What are your thoughts on GPU sharing for short-lived ML jobs? Would you think it's better to get it done faster or have a higher bandwidth? So I think by short-lived ML jobs, you mean multiple or in parallel running machine learning experiments, for example, or for training. I would suggest that get it done faster would be a better thing than deploying multiple machine learning training jobs onto the same GPU. Of course, this changes from use case to use case, but in general, my advice would be to get it done fast. You can also, if you see that model doesn't converge in a given time period, you can also cancel and deploy the next job. And I cannot see any other questions here. All other questions I have put an answer on it. So I think I can end this session here. Wayne, thanks very much for joining again this session. It was great to be here in this virtual event, and have a nice virtual event in upcoming days. See you. Bye-bye.